Hello everyone, I'm Arun Purohit. Welcome you all in this series of short video lectures on quality management. In this video, we will discuss control charts for attributes. After watching and learning to this video, you should be able to understand the concept of control charts for attributes. You should be knowing that what are the different types of charts used in this situation. You should be able to prepare P chart and NP chart. In previous lectures, we learned that how do we use different types of control charts for variables. In contrast to control charts for variables, we do not measure any physical quantity to prepare control charts for attributes. That is, in case of control charts for attributes, we do not go for measuring any quality characteristics, or we call it as CTQ. Rather, the product is categorized either as conforming or as non-conforming. For example, if a product does not perform its expected function, then we will categorize it as functional or non-functional, or we can say it is defective or non-defective. So there are only two possibilities in such situation. In many situations, product's quality is evaluated on the basis of many quality attributes. For example, in case of a finished car body, the color of the body and its roughness, and there are many other attributes which will define whether the car body is of okay quality or it is a defective car body. So, for such situations, we use control charts for attributes. We have a variety of control charts which are used for attributes. Following situations that may arise in the population of a production process while manufacturing a kind of product. We may have the product to be of such kind that the units produced would either be defective or non-defective. If we have many non-conforming or defective units in a sample, then we go for preparing P charts. The other kind of product may not be simply assigned as defective or non-defective. Rather, we may have a sample of number of units having number of defects. So instead of having defective units, in this situation we have number of defects, and when we have number of defects per sample, we go for preparing C charts. In other situation, we may also encounter a condition when we measure number of defects per unit, and when we measure number of defects per unit, we prepare U charts. Now let us discuss control chart for fraction nonconforming, or popularly called as P chart. Fraction nonconforming is defined as the ratio of the number of nonconforming items in a population to the total number of items in that population. Suppose in a manufacturing process we manufacture 1000 units, and out of 1000 units, suppose we find that 50 items are defective, then the fraction non-conforming would be given as 50 divided by 1000. Since P chart is prepared for the situation where product is assigned either as defective or non-defective, so since it is having only two possibilities, the process is best modeled by binomial distribution. Binomial distribution is the distribution for such situation, and the probability distribution is given by this expression, where we see that probability of having x number of defective items in a sample of n units would be given as n combination x multiplied by p power x 1 minus p power n minus x, where p is the probability of having defective items and it is a stable value. Mean value for a binomial distribution is given by n into p and its variance is given by np into 1 minus p. We need to calculate fraction non-conforming for the sample, and for the sample it is p cap equal to d by n. Capital D is the total number of defectives in samples of n units. Now let us learn how do we define control limits for p-chart. For that purpose, we first calculate average value of fraction non-conforming, that is p bar. Now suppose we select small m number of samples from a production process and each of the sample was containing n units, and then we evaluate that how many defectives were produced in each of the sample, and then we add up all the number of defective items, that is given by sigma of di, where I changes from 1 to m, that is we sum up all defective items for all of the samples and divide this term by m into n, that is the total number of units produced. Or alternatively we can find fraction non-conforming for each of the sample by dividing the number of defective items d by sample size n for each of the sample, and then we sum up all fraction non-conforming, that is pi cap, for all of the samples and divided by small m. After calculating average value of fraction non-conforming, we can apply these formula for calculating the control limit, and we can see the center line is given by p bar and upper and lower control limits are given by p bar plus minus 3 multiplied by p bar into 1 minus p bar divided by n, where small n is sample size. Friends, we can also encounter a situation where sample size is different for different samples. That means for each of the sample size might not be the same. For such a situation, what we can use? We can do either we can calculate either average sample size, or we can define different control limits for different samples, and then we can prepare the control limits. Now let us take an example for p-chart. Suppose we take a manufacturing process for cans used for packaged juice, and we know the CTQ, that is the critical to quality for a can, would be, is it leak proof or not? If it is leak proof, then it is okay quality, or otherwise if there is some leakage, then can is a defective item. So for this manufacturing process we gather data, and the data are given here. We see that we have 30 samples from number 1, 2, 3 up to 30 shown in first and fourth column, and the sample size is 50, small n is equal to 50. Then for this manufacturing process of cans, we find that how many number of non-conforming cans are manufactured, that is we evaluate di value and record it in second column and the fifth column, and we know that after evaluating measuring the di value, we need to find out fraction non-conforming, that is pi cap, for each of the sample, and for that purpose we divide di by sample size small n. So here for the sample number 1, the total number of non-conforming produced are 12. It is divided by 50, so will provide us pi cap to be 0.24, and in this manner we find 30 different values of pi cap. And finally, in the sixth column, the bottom of the sixth column, we calculate p bar value, that is the average value of fraction non-conforming, by adding all the pi cap values and divide the sum by 30, and that will give us p bar equal to 0.2313. And here we get the control chart, that is the p chart for this example. And what we see, that the center line is given by the p bar value, which just we have calculated, or alternatively we can also calculate it by the summing total number of defectives, that is 347, divided by 30, that is total number of samples, and divided by 50, that is the sample size, and finding the center line to be 0.2313. For finding upper and lower control limits, we use the formula given previously, and then we plot each of the sample on this graph, and we find that two of the samples are having the fraction non-conforming crossing the upper control limits, and that means that the process is not in control, or there might have happened something wrong which created a sample of defective value, that the sample is not having up to the mark value. So removing these samples from our given data set, and then we again calculate the center line and upper and lower control limits, and finding them again, and plot all the remaining 28 data values again. And again, if we find any of the value going beyond upper or lower control limit, then we will remove them, and so as to get stable values of UCL and SAL. And this way we prepare P chart. Now, instead of using fraction non-conforming value, that is the P cap value, we can also find the total number of non-conforming for each of the sample. And if we prepare a control chart for such a situation, we call it as NP chart. So NP chart is basically same as the P chart, but in P chart we use fraction non-conforming, whereas in NP chart we use number of non-conforming, that is we use number, not the fraction. And here the upper and lower control limits and the center line are given as depicted in the box. This control chart is based on number of non-conforming rather than the fraction non-conforming. Otherwise it is same as P chart. So here we conclude this short lecture on P and NP chart. In the next lecture, we will discuss C chart and U chart. Thanks.